Okay, so this is for chapter 20, the practice questions. Okay, so we'll start on the first question. The first question is regarding what element is being reduced in the following reactions. So give you the reaction is 2Br1 negative aqueous plus H2O2 aqueous plus 2H plus aqueous produce Br2 aqueous and 2H2O liquid. So ask us to identify what element is being reduced. So what we do is start with sign the oxidation numbers. So follow the rule, we can say this Br here is a monatomic ion. So the oxidation number is -1. And in H2O2, we will see the H is +1. Oxygen will be -1. So this H plus is also monatomic ion. So the oxidation number, same as the charge number, so +1. Here on the product side, we have Br2 aqueous. So Br2 or O2 and N2, those are diatomic elements. Element has oxidation number equal to 0. So this is 0 for both Br, 0. So the last product is H2O, and in H2O, H is +1, oxygen -2. All right, so once we know the oxidation number, and we can say oxidation number of oxygen changed from -1 here to -2 on the product side. So therefore, oxygen has been reduced. So your oxidation number for oxygen gets lower. So therefore, oxygen has been reduced. And where is oxygen on the reactant side? So oxygen is in H2O2. So if you have some of those compound or ion have the element that has been reduced, then that compound or ion is the oxidizing agent. So we already answered the question, which one has been reduced to oxygen, so therefore the answer is B. But just as a practice, so therefore, meanwhile, bromine's or Br's oxidation number has changed from -1 here to 0 here. So therefore, bromine has been oxidized. And then where the bromine occurs on the reactant side, it occurs in the bromide Br1 negative aqueous. Therefore, Br1 negative aqueous is the reducing agent. So that's not relevant to this question, but just to practice possible other way to ask those questions. So therefore, we identify both who has been reduced and who has been oxidized, and also what is our oxidizing agent and what is the reducing agent. So next question, question 2, is give you this overall equation. You want to balance this equation by the method of half reaction way. And then after that, want you to identify the coefficient for the Cl2 gas. So to balance redox equation by the half reaction method, following those steps. First step, you write or rewrite the given overall equation as oxidation half reaction and reduction half reaction. So the oxidation reaction for this given equation, you will see it will be Cl1 negative Cl2 gas, because Cl1 negative has the charge -1, and Cl2 gas has oxygen number 0. So therefore, the oxidation number for Cl increases. Therefore, Cl has been oxidized. We identify or we write this oxidation reaction in this equation. Okay, sorry, here I forgot to change, just copy and paste. So this will be the reduction reaction. So reduction reaction happens for this Cr2O72 negative because we can identify in Cr2O72 negative. So here the oxidation number for Cr for the chromium is positive 6, and then here the positive 3. So therefore, the oxidation number for chromium goes down. So therefore, what happened to chromium is chromium has been reduced. So we write this half reduction reaction and half oxidation reaction. Then we'll follow this next few steps to balance the equation. Okay. So step number 2 is you want to balance the equation. So you will write one equation, let's say the oxidation equation. It is Cl1 negative equals, so let's say produce Cl2 gas. So you follow the procedures. The next procedure tells us balance atoms that are not O or H. So in this problem, the atom that is not O and H is Cl. So Cl on the right, we have 2 Cl. On the left, there's only 1 Cl. So therefore, we will put a coefficient to balance the number of Cl atoms. So therefore, we will put a 2 here. So now we have the atoms that are not O and H balanced. And so this finished the second step for the oxidation reaction. And let's see, for the reduction reaction, we will have that Cr2. Let me erase those. Or we'll use the same color for the equations. Okay, so where's my... So we'll use this one. Okay, so let's see, our reduction equation is Cr2O7 2 negative equals, and let's see, produce the Cr3 plus equals. Okay, now we want to balance the atom that is not O and H, and which you can see will be the Cr, the chromium. Okay, so chromium on the left side, we have 2 chromium. And so if you want to balance the chromium, you can just use the coefficient here. So you put a 2 here, so that will balance the Cr. So that's finished the second step for both reactions. So let me erase some of those names, and then we can have more space to write something else. All right. So now we want to go to the next step. Okay. So the next step is step 3. So you want to balance oxygen by adding H2O. The first equation that we don't have oxygen, so therefore we will skip that. The second reaction, we see we have 7 oxygen on the left. You want to balance the 7 oxygen, you are adding 7 H2O liquid. Okay, so therefore we balanced the oxygen atom. We have 7 on the left, 7 on the right. The problem is when you introduce or when you adding water, you simultaneously also adding H. So therefore you will go to the next step. said before, to balance H by adding H plus aqueous. So we're counting how many H plus on the right. In this example, we have 7 times 2, so 14H. So what we do is, let's see, adding 14H plus at the state with AQ on the left. So in this way, we balance both oxygen and hydrogen. So now, in these two equations, all the atoms are balanced. So we'll go to the next step, balance the charge by adding electrons. And let's say the first equation, we have 2 chlorides. So 1 chloride is -1. So 2 times -1 gives us -2 on the left. So therefore, we were adding electrons to balance the charge. So 1 electron has a 1 negative charge. So here you have -2. So therefore, we put a 2 here. Now we have also -2 on both sides. And erase this -2, -2, so we don't confuse by that. So therefore, the first equation, everything is balanced. The atom are balanced, the charge are balanced. So the second equation, we will see how many charge on this right side, 0 charge from water, and then we see how many charge on the other one. So 0 charge from water, but the chromium-3 ion, so 1 ion has a 3 positive charge. We have 2 chromium-3 plus ion, so therefore we have +6 charge from the first product. So altogether, 6 plus 0 equals +6 on the right. And then on the left side, let's starting from the first reactant. So we have 1 Cr2O72 negative, so that will give us -2. Then we have a 14, I should write H plus. We have 14H plus. So therefore 14 times plus 1, so we get +14. So +14 and then -2 to give us +12. So obviously right now we have +12 on the left, and then we have +6 on the right. So the charge are not balanced. So you adding electrons to reduce the +12. And 1 electron has 1 negative, so therefore we need to add 6. All right, now all the atoms, all the charge are balanced. So if we erase all those, and then we will have our balanced 2 half equations. So what you do next is make sure in both equations, they will have the same number of electrons, then you adding them together. So you can see this first equation has 2 electrons. The second equation has 6 electrons. So to make them have the same number of electrons, you multiply the first equation by 3. And then that will make the first equation become, let me change it back to the red color for our reaction, for our equations. Okay, so we will have 2 times 3 is 6, so 6 Cl1 negative aqueous, then produce 3 Cl2 gas, then plus 2 times 3, 6 electrons. All right, we don't have to do anything in this example to the second equation, because the second equation already have 6 electrons. Okay, now we can add. We can add in these two together. And when you add in 2 together, you will see you cancel same species on opposite side of the arrow. You combine same species on the same side of the arrow. And you can see our arrow is here. So on the left side, maybe we'll just write them just one more step. We take a 6 electron plus Cr2O7, 2 negative aqueous plus 14 H plus aqueous. So these are the 3 reactants from that equation. When you add the equation, you add in all the reactants together. So we have 3 reactants from this equation. Then we will plus whatever the reactant in the other equation. So in the other equation, we have 6 Cl, 1 negative aqueous. Now that we're adding up all those reactants from both reactions. So therefore, we draw the arrow. Then we add in the product. So one product we have is 2 Cr, 3 plus aqueous. And then we will have 7 H2O liquid. So that will finish the 2 products from that equation. Then adding the product from the other equation. So there are 2 products from the other equation. The first one is 3Cl2 gas. The other one is 6 electrons. Yeah, so this preliminary is the result after we adding the 2 equations. So what you do now is to see, do we have something same on the 2 opposite side of the arrow? We do, because we have a 6 electron here on the left side of the arrow. We also have a 6 electron on the right side of the arrow. So therefore, this 6 electron comes out. And I think that's it. Then we will check, do we have something same on the same side of the arrow? We don't. So therefore, this is the final preliminary result after our balance. And then you will check, see if every atom is balanced. You begin by whatever you see first. So you can see you have Cr. So I write Cr. Now how many Cr on the left? See, the Cr only in this ion, and therefore we have 2 Cr. How many Cr on the right? Cr here in the 3 plus ion, not in those, so therefore there's also 2. So next, it will be oxygen. How many oxygen on the left? Oxygen only appears in this ion, not in this, not in this. Therefore, we have 7 oxygen. How many oxygen on the product side? This is not oxygen, so there are 7 water, so therefore give us 7 oxygen. And then let's check the next one will be the H. So how many H on the left? We have 14 times H plus, so therefore we have 14. How many on the right? 7 times 2, we have also 14. So the last one with the Cl. How many Cl on the left? You can see we have 6 Cl and negative, so we have 6 Cl. And here I have 3 times 2 on the right. Product also 6. So therefore all the atoms are balanced. But you also need to check the charge. So let's see the charge. How many charge on the left? Well, here is the 2 negative, and then 14 plus, and then 6 negative. So therefore we get negative 8, and then we get, so they all this together give us positive 6. So positive 6 on the left side. Let's see how many charge on the right. So here is 2 times 3 plus, give us positive 6. And here's 0, and here's 0. So therefore on the right, also positive 6. Okay, so then we check this equation as written and circle that we already cancel out the electron. So what I circle in the blue is the net equation that is balanced. So everything is balanced. And then the question is asked us, after we balance the equation, what is the coefficient for the Cl2 gas? Okay, so what is the coefficient for Cl2 gas? And we can see, go back to the equation, check the coefficient here is 3. So therefore, the answer is C. Okay, so next question, question number 3. We are given an oxidation reduction reaction given by this equation. So then tell us this equation is spontaneous. So therefore, if we use this equation in a voltaic cell, electrical current can be generated, indicating the reaction occurs at the anode. We have this few choice. Then we know in a voltaic cell, all we have to memorize, oxidation reaction happens on the anode, reduction reaction happens on the cathode. So therefore, what we need to do is to identify the oxidation, the reduction reaction in the given overall equations by using the oxidation numbers. So we copy this overall equation from there and put it here. Then we assign the oxidation numbers for all the atoms. So we begin with this Cr2O7 two negative ion. So we can say in this negative ion, and we will assign Cr will be the positive 6, so oxygen will be negative 2. So then this H plus is monatomic ion is plus 1. I1 negative also monatomic ion negative 1. So therefore this one also plus 3. And this I2 the element is 0. So in water you have H will be plus 1, oxygen will be negative 2. Okay, so after you assign those numbers, then you can see for the iodines, it goes from negative 1 to 0. So therefore, oxidation reactions is this 6 I1 negative equals produces 3 I2 solid and plus 6 electron. So then, how do you know there's a 6 electron? Well, you go by the charge. So you have a 6 I1 negative, you get 6 negative on the left. So therefore, you have to add in 6 electrons to balance the charge. So then the reduction reaction will be those Cr2O7 2 negative plus 14 H plus well, there in the equation you don't see the 6 electrons. Then you know why you adding 6 electrons, because if you copy that 2Cr3 plus equals plus 7H2 liquid, then you know you will get a plus 6 charge on the right. So if you don't add in the electrons, so you get a positive 14 from this, negative 2 from this. So therefore, we have adding negative 6 to balance the charge on the left, on the right. Okay, so therefore we identify our two reactions. The reduction reaction will be this reaction at the bottom. The oxidation reaction will be the one on the top. And then the question just asks you, so what reaction occurs on anode? So as I said, you try to memorize those kind of rules or conventions. So we will see oxidation reaction happen on the anodes. So therefore, oxidation reaction is this. So therefore, this happens on the anode. Happens on anode. So therefore, the answer is A. Okay, so next question, question number 4. Using the data in table 20.1. So I have a part of the table 21. So in table 21, give us those E0 reductions. So the so-called standard reduction potentials. You can use those numbers to calculate the standard EMF, and so standard is represented by the 0, and then this cell is the overall equation like that. So to do that, you need to follow a few steps. So if I not give it to you, you have to pick up from the table what are the data. What are the standard reduction potentials? So we see in this equation, we have Ag, we have zinc. So this is kind of simple, just zinc metal and silver metal. So therefore, we pick up these two half reduction reactions, get the number from the table. Then from the given overall equations, we can see we have 2 Ag plus iron plus zinc solid plus 2 Ag solid plus zinc 2 plus iron. And if you go by the oxidation number, so you see this Ag plus will be plus 1, here is 0, then here it becomes 0, then here plus 2. So you can see the oxidation number for Ag changed from plus 1 to 0. So therefore, Ag has been reduced. So the reduction happens, so this reduction reaction will happen on the cathode. And we check the oxidation number for zinc changed from 0 to plus 2. So therefore, zinc's oxidation number increases, and zinc has been oxidized. And we know oxidation happens on the anode. So those are important because in order to use this equation, you have to know who has been oxidized, who has been reduced. So the one has been reduced on the cathode. So you will use this number like E0 reduction on the cathode, just take this number, then minus the number for the reaction happening on the anode. So on the anode, we'll have the oxidation reaction. So even though in the oxidation reaction, so if you write oxidation reaction in this from this overall equation, you will see that will be this equation. So zinc solid produces zinc 2 plus iron aqueous plus 2 electrons. So then you compare this one with those equations you get from the table is opposite, which means the reactant here is actually the product in the equation from the table, then the product in the equation you write from this given equation is the reactant from the in the equation from the table. So that's the way, but you don't have to do anything else. Just know if you have the oxidation reaction, when you try to compare the equation from the table, you will see the way they write the opposite. So just using this number and then put it in the formula. So therefore, we know our reduction reaction is that one. So our reduction reaction has happened on the cathode. So that's the reduction reaction. The Ag part is the reduction reaction, which has this theta positive 0.80 volts. Then minus is from the formula. So what on the anode? On the anode, we have this zinc being oxidized. So then zinc being reduced has this potential, negative potential. So therefore, you will just minus the negative 0.76 volts. So that becomes 0.80 volts plus 0.76 volts. And that means we get 1.56 volts. So this, you check the answer, I think that answer will be B. Yeah, so the answer is B. Okay, so next question, number 5. So similarly, so based on the table in table 20.1, which of the following species were you expect to be the strongest oxidizing agent? And so we know the species on the top of the left side of those equations in the table are stronger oxidizing agent. So what that means, you will see the arrow here for every half reaction written in this table. So what I mean, the left side of the arrow. Then you have those near the top. Then you see there's a bottom. Okay, so the rule is, so if you go to the top and see the left side, some of those species, maybe ion, maybe molecular compound. So they are stronger oxidizing agents. So in this table, we can see on the topmost is F2 gas. So therefore, F2 gas in this table is strongest oxidant or oxidizing agent. But for these given few choices, we don't have F2. So the first one is Cl1 negative. So Cl1 negative, it not appears on the left side. It actually appears on the right side of this equation. So if we sum those choice is on the right side of the equation, they cannot be our answer. They cannot be the strongest oxidizing agent. So therefore, the first one not the answer. The second one have H2 gas. So where's H2 gas? H2 gas. H2 gas is here, and that is also on the right side. So therefore, that is not our answer. The next choice is O2 gas, as I talked about in the lecture. So we have quite a few O2 gas. So there's O2 gas here, and there's O2 gas here. I think there's another O2 gas here. So what you use, what depend on what you want to compare. You want to compare with if everything else is in a kind of neutral environment, you want to use the oxygen in a neutral environment. So this environment is acidic. This also acidic. The difference between these two is the concentration. So this one is concentrated acid. This one is diluted acid. And we have made our environment even more acidic. So this one have water. So this one you can see pretty much pH neutral. So if everything else also pH neutral, so you want to compare the number for O using this number. Okay, so far we get that's not our choice because they are on the right side. The right side of equations in the table. So they cannot be the choice of a stronger oxidizing agent. So far we get O2 is the strongest one because the number is 0.40, or we don't have any other choice. So next on the list is H+. So where's H+? H+ is here. So that's on the left side. That's a possible choice. But by definition, that's 0. So therefore, they're all near the bottom. The one on the top is stronger. So then the last one is Na. We have Na here, so Na even more to the bottom. So therefore, just these three possible. So therefore, the one on the top, or the one has the more positive number, is O2 gas. So the answer is C. The answer is C. Okay, so question number 6 is using those data from the table we just talked about to calculate a standard free energy chain delta G and the equilibrium constant K at 298 Kelvin for this overall equation. Okay, so you just identify, follow a few steps. From the table, we first identify the two possible half reaction we're going to use. So one is Ag with Ag something. Okay? You can see here Ag solid, Ag plus. Even though we write in the opposite way as the equation get from the table, but you see here Ag solid become Ag plus ion. In the table, you do the opposite. So Ag plus ion plus electron produce Ag solid. Just just take those equations from the table, write it up the number, don't do anything, and then you just identify in this OR equation. So what really happen on the cathode, what really happen on the anode. So our convention is oxidation reaction happens on the anode, reduction happens on the cathode. But to know who is oxidation, who is reduction, you have to use the oxidation numbers. So oxidation number for this Ag solid is 0. For O2 gas also 0. For H plus ion plus 1. So for Ag plus ion plus 1, then for H2O, the H in H2O is plus 1, then oxidant -1. Okay. So once we know that, and we can see what happened to Ag. You can see the oxidation number for Ag changed from 0 to plus 1. So therefore Ag has been oxidized. And then we know oxidation reaction happens on anode. And then we also know the oxidation number of oxidant changed from 0 to -2. So therefore oxidant has been reduced. Then we know the reduction happens on the cathode. So now we know who is on the cathode, who is on the anode. So what it means is this will be on our cathode. So this will be on cathode, and this will be on the anode. Okay. Then you get just using their numbers. So if you know you have this on the cathode, so the formula tell you take the number from the cathode first, so that we get positive 1.23 volts. Then subtraction from the formula, so the subtraction sign here. Then take the number for the reaction on the anode. So that's on anode. So therefore minus positive 0.80 volts. So therefore we get positive 0.43 volts. All right, so after we get this, then next you want to use this equation to calculate delta G, or delta G naught, which means delta G at a standard condition. So just go by this formula. The formula tells you there's a negative sign. Then the next is N. So what is N? N is number of electrons involved or transferred in overall equation. Okay, so in overall equation, well, you can see in the half equation, so you have 1 electron and then 4 electrons. So then in the overall equation, you go by, let's say the easy way is to go by how many Ag. So we can see we have Ag, 8 Ag atoms, then 8 Ag plus ion. So how can we change, or how can the Ag change from atom to ion? So therefore, obviously lost electrons. Then 1 Ag atom lost 1 electron, become Ag plus. So we have 8 Ag atom become 8 Ag plus ion. So therefore, the electron transfer is 8. So for this problem, we identify N is 8. And 8 what? So 8, we say 8 moles. Okay, because all those coefficients in the equation, you can think about either like just one number, one ion, or how many moles of ion. All right, so we get 8 moles of electrons. So therefore, this is N. The next one is F. So F is a Faraday constant. So that is the 96,485 coulombs over 1 mole electrons. So then next, we'll see that E0 cell. So this is the next number, E0 cell. So this is this one. You just put in, so 0.43 volts. Okay. So now what you do, you can change the volts. So we know volt equals Joule over coulombs. Okay. Just think about a unit. That is a unit. All right. So therefore, we can change these words as Joule over C. C means Coulomb. Okay, so let me do this way and get my J over C. Then you see the constellation of the unit. So this mole here comes out, this C here comes out, get a Joule, which is a typical unit for energy. All right. So therefore, we do the calculation, multiply and divide. So what we get for this, for those, so let me see, I get negative come from this negative, okay. 3.1908. What's the unit? Joule. Okay. So once we have the delta G 0, we can use this equation to find K. So we go by substitution. So let me go back to my red pen. Okay, so I have negative 3.1908 J. So that's for delta G naught equals negative R is 8.314 unit J over mole over Kelvin. So this R. The T is the temperature in Kelvin. We are given 298. You probably want to use 1.5, but those numbers become very need to be very precise. So then L and K. All right. So what do you do next? Just take a few. So take this number divided by these two numbers. So negative 3.1908 J. Then divided by this. So before we divide by this, we can see the constellation of the units. So there's a K here. Okay, so the K here comes out. Now we have the problem is there's a mole. So where's the mole? So you know the K has those exponents, okay? So the K, let's see. So if you write K as the product concentrations over reactant concentrations, and sometimes you don't write the exponent because they are 1, but even they are 1, they have a unit. So the 1 comes from coefficient. So all the coefficient has a minimum moles. So therefore there's a mole here. And then when you take, let's say, Ln K, so that will become Ln the product mole and then reactant moles. So that will become, by using mass rule, so Ln product, then the mole will flip to the front. So the mole will become here, mole equals mole like that. So I can use this. So then minus the same process moles times Ln the reactant. So therefore, you will have a mole for both of them. So therefore, when you have Ln K, actually you will have a mole come from those Ln K or Ln Q. So once we have this mole, then this mole will cancel out with this mole. So now we have only the J left over. So therefore, we'll divide by these two numbers multiply, and now we know the unit will be our J. Okay, so 8.3 or negative 8.314 and then 10 times 298.15. So now the unit is J. So J and J cancel out. Then we have this on this side. We do the same divide to L and K. All right. So let me erase some of those. We don't need those, and then we'll finish our calculation for the K. It turned out the K is kind of a gigantic number, so therefore you probably have to keep as much as possible the precisions. Okay, so once you have this equation and after you divide, I don't know why I use so difficult. Okay, let me go back to my pen. All right, so after I divide this number by these two numbers, so I get a positive 133.965 equals L and K. And then next, you take the exponential, then exponential with Ln cancel out. Then you take the exponential of this number, so you get 1.5 times 10 to the positive 58. Then that equals to K on the right. So that's our answer for the K. And then this question has like two parts. Ask you not only K and also the delta G. Okay, so then the delta G. So what do we get for the delta G is this number. So the problem is I write only J, and then you convert this into KJ. So that's easy. So this J, the decimal point is here. You move the decimal point 3 times to the left. So therefore you get negative 332 kJ. So the answer has a per mole. What they mean by the per mole is you have this negative 332 is for this equation as written, which means you have 8 Ag solid atom plus 2 O2 gas and so on. So that's what they mean by the per mole. So therefore the answer, we have 332 for the delta G. Those are the only one choice, but we confirm we have this answer for the delta G. We have this number for the K. So therefore our answer is E. Okay, so next question number 7. You want to, let's see, the question number 7 is consider a voltaic cell whose overall reaction is this. Then at 25 degrees Celsius, what is the EMF, which means what is the delta, what is the E cell? What is E cell for this voltaic cell? So not E cell 0 because those conditions not standard. Okay, so what we do is if I give you those half reactions, so then you just say for the from the given overall reaction equation, from this overall equation I copy here, you can see that the oxidation number for TB changed from +2 to 0, so therefore TB has been reduced. The reaction will happen on the cathode. So we also see the oxidation number for zinc changed from 0 to +2, so therefore zinc has been oxidized, and then this zinc reaction will happen on the anodes. So therefore, so let's go back to these two equations given. So we see this lead has been reduced, so therefore this on the cathode. So this on the cathode, and this on anode. So therefore we can use the one on the cathode use number just straightforward, so therefore negative 0.13 volts. Then subtracting from the formula, then the equation on the anode. Equation on the anode has negative 0.76 volts. So therefore you get negative 0.13 volts plus 0.76 volts. So minus become positive. So what do we get? So what it gets is positive 0.63 volts. Okay, now this is the E0 cell. Okay, so this question asks you E0, E cell, not E0 cell. So then what you do, just use that person's name equation. So that's not N, Nernst equation. So that's written as this. So you have E cell equals E0 cell, okay? Then minus RT over NF ln Q. Okay, so Q is the reaction quotient. So Q is reaction quotient. It has similar expression as K. Okay, so as for this overall equation, Q over equals product over reactant. Our product is zinc 2 plus. Our reactant is Pb 2 plus. We have other reactant, other product, but they are solid, so they are not in the equation. Right? So now you use those given concentration to calculate the number for Q. So the number for zinc is 0.35. The number for lead is 1.5 times 10 to the negative 2. And you divide, multiply, so you get a number for Q. So the Q becomes 23.3333. Okay, now we have all the number we need. So we have E0 cell, which is a positive 0.63 volts. Then we know R is 8.314. So I will skip the unit now. You can check the unit from the previous questions. Then you will know this also get volts. So this is also 298.15. And then N, the problem is N. So now N is the number of electrons in this equation. So for this equation, N is 2 electron transfer. So therefore, we have 2. And then F is 96,485. So those numbers multiply and consider with another more from this Q. So that will give you the watts. Okay. So watts is the unit. Then R and Q. R and Q has a number now 23.3333. Right. So with those numbers, so this way here, the unit. Let me just use a different pen. So this is the unit. And this is unit. Watts. All right. So now let's say we have a positive 0.63 volts, and then those numbers multiply, and you get 0.012846 watts. Then the Ln 23.3333. So we then take one more step, 0.63 watts positive, then minus 0.0405 watts to get positive 0.59 volts. So you check the answer in E. Okay, so next question is if the potential of a zinc H2 cell, like the one shown in the picture, is 0.55 volts at 25 degrees Celsius, and when zinc 2 plus ion concentration 1.0 molar and partial pressure of 82 is also 1.0 atm, ask you to calculate what is the pH in this solution. So what is pH here in this solution? So from the table, we know the two half reaction standard potential is H plus plus electron plus 1 electron, 2H plus 2 electron plus 82 have this 0 by definition. Then zinc will have this negative 0.76. So now from the picture, we can see anode is here, and cathode is here. So the picture tells you clearly, so this happens on the anode, we have this zinc oxidized. So therefore, this is on the anode, and this on the cathode. So therefore, the next step, just take those numbers on the cathode, have 0, then minus the number for the anode, that is 0.76 volts. Therefore, positive 0.76 volts. And this is E0 cell. So next, use nearest equation. So that equation tells us E cell equals E0 cell minus RT N F L N Q. So now let's substitute those numbers, and then we try to first find out the Q. So we have the number for the E cell. The number for E cell is 0.55. Okay, so 0.55 volts equals 0.76 volts minus 8.314 times 298.15. Then you have to find out for this equation. Is when it happens, what is the number of electron transfer? So this both half reaction has 2 electrons, so your overall reaction will have 2 electrons. If one has 5, the other one has 3, then your total number of electrons will be 15. So if one has 6, the other one has 3, then your total number of electrons is 6. So 96, 4, 85 is very deep, then L and Q. All right, so you just start calculating those numbers. So let's see, first see if I subtracting 0.76 here, subtracting 0.76 here, so this comes out, then you will get negative 0.21 on the left, and then you have negative this number, so 8.314 times 298.15 divided by 2 divided by 96,485, and then times L and Q. Okay. All right. So this is still negative 0.21. Then those numbers multiply and divide, so become negative 0.0128 0.839 then times L and Q. Okay. So therefore, you will take a negative 0.21 divided by negative 0.012839 equals L and Q. And okay, kind of run out of room here. Okay. So now, so you take this number divided by that, you get 16.356 equals L and Q. So as you know, you can take e to the power 16.356 equals e to the ln q. So e to the ln cancel out, and then you will get q. So these two, because they are anti-function each other, so they cancel out, and so therefore you get a q on the right. So q on the right. Then here you use the calculator, take the exponential, so you get 1.269 times 10 to the positive 7. Okay. Now let's go to see our equations. So this on the cathode and anode. So when you have these two equations and or have these two equations, one have on the cathode, one have on the anode. So if you add them together, you get the overall. The overall reaction is zinc solid plus 2H plus aqueous produce zinc 2 plus aqueous, then plus H2 gas. So this over equation, so we have two product, two reactant, and then what is our Q? So Q will equals product on the top. For the gas, you use partial pressure, so we see partial pressure of H2, then times the molarity of zinc 2 plus, and then divide by the reactant molarities or partial pressures. So for H plus, you have the coefficient 2, so therefore square. Zinc not in the equation because zinc is solid. All right, so now we know what our Q looks like. So therefore we put here. So we say Q equals the partial pressure of H2 times molarity of zinc 2 plus, then divided by molarity of H plus squared, then that equals 1.269 times 10 to the 7. So just a few more steps. So we are given some of those informations. We are given what is the partial pressure of H2, which is 1. What is the molarity of zinc, which is 1. The only number we don't know is H plus. So therefore, you're solving this equation. So H plus squared equals 1 times 1 is 1, then divided by 1.269 times 10 to the 7. So that's become 7.883 times 10 to the negative 9. So obviously, you just take the square root. So H plus become square root 7.883 times 10 to the negative 9, and you take the square root, so that become 2.81 times 10 to the negative 4. So then we know we want to find out the pH. So pH equals negative log of H plus polarity. So then we just plug those numbers in. So 2.81 times 10 to the negative 4. That will give you 3.5. So let's see the answer. Go back to the A. All right. So next question, question number 9. So ask us to calculate the time, how much time is needed to deposit 1.5 gram of chromium metal from an aqueous solution of chromium 3 chloride using a current of 1.6 A. A means ampere. Ampere means coulomb over second. So you can just use a few conversion fractions as we studied in today's lecture. So let's starting with 1.5 gram of CR and use our usual way. We first using molar mass of chromium. So 1 mole of chromium is 52.0 gram. So next, you will use, so you will cancel out a gram, get more of chromium. The next, you want to use the ratio between the chromium ion or solid and the electrons. Okay, so you want to deposit, which means reduce. Reduce the chromium 3 plus ion to chromium solid. So therefore the equation will be Cr3 plus aqueous plus 3 electron to produce a Cr solid. So once you have this equation, then you know the coefficient between the chromium 3 plus or chromium solid. We did not use chromium plus, just use chromium. The chromium coefficient here is also the same. Let me emphasize that. So the coefficient here 1 and 1. But here is 3 for the electron. Okay, so therefore we write 3 moles of electron. Okay, so let me emphasize, so where are those come from? Okay, so this 3 come from this 3. This 1 come from this one. So next, you use the Faraday number. So 1 mole of electron is 96,485 coulomb. Next, you use the given ampere. So when you have 1.6 A equals 1.6 C over second. So you want to count out the C. So therefore put 1.6 C at the bottom, then 1 second. So then let's just say we need 1 more fraction. So if we check the concentration so far, we'll get a second. But the question all in minutes. So the gram here comes out, more here comes out, more electron comes out, C comes out, get a second. So I run out of space here. I will write on the next line. So just multiply by another fraction. which means you want to get minute. 1 minute is 60 seconds. So therefore, this second here comes out with this second. So you get 86.975. You run into 87 minutes. So therefore, the answer is E. So the last question is conceptual. So ask you what in the Voltaic cell, where the oxidation reaction happens. So just review that. You can see oxidation reaction happens on anode in Voltaic cell. And reduction reaction happens on cathode. So therefore, the answer is B. So if I ask you another way, so what reaction happens? Where the reduction happens? So the answer is A. So what does salt bridge do? Salt bridge is used for or to migrate ions to balance charges, not to balance charge on the equation, to balance charge physically on those in those solutions. So on the anode and the cathode. Well, external wire for the electron to flow. Okay, so that's it for chapter 20.